Good evening everyone, this is Ranjana Goswami. I would be talking about a nucleus, something which is of great interest and something into which everyone looks with great awe and with great admiration. What is a nucleus? Why is it so different from any other element or any other particles of the world or universe? Let's just go into it a little bit. Well, if we just keep on studying the properties of the nucleus, what we would observe several things, and the interesting part of the whole story is that it's way different from the properties that we know of. If we just start off by looking into the size of a nucleus, as we all know, it's many times less than the size of an atom. If we look into the radius of the nucleus, well, it's given by r e to the power 1/3, r naught e to the power 1/3, where a is the mass number and it is only about few Fermi. Okay, and the interesting part of the whole story is that the force within which this nucleus or the nucleons exist within the nucleus is one of the strongest force of the nature. There is no known force in the entire universe discovered till date which is stronger than the force that exists within that extremely small radius of 1.5 Fermi. Okay. Now the nucleus or fermions within the nucleus plays a significant role in the formation of this nuclear force. In fact, they are the ones who play a pivotal role in this formation of the strong nuclear force. Well, the next thing that we need to look into, therefore, is the corresponding nuclear potential, because the nucleons within the nucleus actually exist within a nuclear potential. Interestingly, this nuclear potential is very much different from the potential of the electron of an atom, which we know of from our regular knowledge of quantum mechanics. Now, the reason is that, as it's well known to all of us, that electrons are actually under a Coulombic force, which is known to be much weaker than the nuclear force of the nucleus. But an interesting point to point out at this juncture is that both electrons and nucleons, they are all fermions, forming the same formed by the same Fermi particles. This potential is short range, and because the nuclear radius is short, this potential is sharply cut off after a radius of the order of 1.3 Fermi. The potential of within a nucleus is a central potential having a 1 by r square difference. The entire potential and its strength, as we can very well understand, depends on the number of nucleons that essentially form the nucleus. So that is interesting, that nucleus consisting of nucleons. And what are the nucleons? They are nothing but neutrons and protons which exist within the nucleus. They play a significant role in the formation of the potential within that very short distance of around 1.3 to 1.5 Fermi. Now, the obvious question that comes up after that is, then obviously these nucleons, they just don't run out of the nucleus, they are bound. So there must be something called the binding energy, which is binding all the nucleons within the nucleus. This binding energy of the nucleus is the difference between the total mass of all the nucleons making the nucleus and the mass of the bare nucleus. If we plot the binding energy per nucleon, then we see that after a certain mass, the binding energy is more or less constant. That means once after a mass of around 20, 25, we'll see that the binding energy takes a more or less constant value. This constancy of the binding energy plays a significant role, a decisive role in deciding important properties of the nucleus, like the stability of the nucleus. If we look into a nuclear chart, we would see that not all nucleus lying within the nucleus chart are stable. Now, this criteria of the stability of the nucleus essentially depends upon the binding energy, which tells us which nucleus under what condition would be stable or unstable. And we also find that the nucleon number plays another significant role in deciding whether a nucleus would be stable or not. For nucleus having even number of nucleons, that means even number of protons as well as even number of neutrons, the nucleus is supposed to be more stable. For nucleus having even number of protons but odd number of neutrons, maybe it's not even. They are also stable, but nucleus with odd number of protons and odd number of neutrons, they are the number of such nucleus, number of such stable nucleus is not very high. It's quite low. So there are certain reasons for which the stability of the nucleus varies as we keep on changing the number of nucleons within the nucleus. Okay.